Have you ever stopped to think about what's actually going on inside a database? I mean, they literally run the modern world, from your bank account to your social media feed. But what if I told you that every single one of them, no matter how huge or complex, is built on just a couple of super simple ideas from math? Well, today we're going to pull back the curtain and uncover that hidden logic that powers, well, everything. Okay, so we've all seen something like this, right? A basic spreadsheet, a list of students. It's organized, sure, but it's not exactly powerful. So what's the secret sauce? What's the magic ingredient that transforms a simple list like this into a rock-solid powerhouse database that can handle millions of people without even breaking a sweat? That's the big question we're here to answer. And believe it or not, the answer starts right here, with just two fundamental building blocks from the world of math. And don't worry, I promise this is the easy stuff. But you have to understand these two ideas, because they are the absolute ground floor of everything that's about to follow. First up, we have the set. Now, a set is just a collection of things, but it plays by two very strict rules. Rule number one, every single item in the set has to be unique. No duplicates allowed. And rule number two, the order doesn't matter at all. The set red, green, blue is exactly the same as the set blue, red, green. So, the two words to remember are unordered and distinct. That's a set. Now, our second building block is the tuple. And a tuple is pretty much the exact opposite of a set. With a tuple, order is everything. The tuple 1, 2 is a completely different thing from the tuple 2, 1. And unlike a set, duplicates are totally fine. So think of it like a very specific ordered list or a sequence. So let's just put them side by side so this really sinks in. A set is like a bag of unique items. The order you pull them out doesn't matter. A tuple is like a specific combination. The order is critical. One is all about unique membership. The other is all about a specific sequence. Got it? Good, because these two are about to become very, very important. All right, so we've got our building blocks, sets and tuples. Now for the fun part. Let's see what happens when we start combining them to create a whole universe of data. Before we can build anything, we need to define our materials, right? In the database world, we call that a domain. And a domain is simply a set. See, there's our first building block again. It's the set of all the approved allowed values for some piece of information. So the domain for grades would be the set containing A, B+, B, and so on. If it's not in that set, it's not a valid grade. Simple as that. So what happens when we take two different domains, say a domain of students and a domain of blood types, and we smash them together? Well, you get something called the Cartesian product. This is a fancy term for a very simple idea. It generates every single possible combination between the two sets. So you get Alice with blood type A, Alice with B, Alice with O, Alice with AB, and then you do the same thing for Bob, and then for Charlie. You get this explosion of possibilities. But this creates a huge problem. Yeah, we've created a universe of every theoretical possibility, but in the real world, a person only has one blood type. Most of these combinations, like Alice being paired with blood type B, O, and AB, are just plain wrong. They're meaningless. They're just noise. So how do we cut through all that noise? How do we get from this chaotic mess of possibilities to just the useful information, just the facts that actually represent reality? Well, this is the real magic trick. And boom, here it is. This is the aha moment. We create something called a relation. And a relation is just a subset of that giant, noisy Cartesian product. We literally just throw away all the combinations that don't make sense, and we keep only the ones that are true. So in this case, we're left with just three valid pairs. We've found the signal in the noise. We've created order out of chaos. So to put a formal name on it, a relation is a subset of a Cartesian product. But what does a relation look like to you and me? It's a table. That's it. It's just a clean, simple table where each row is one of our tuples, an ordered list of values that represents a single real-world fact. That is all a database table truly is. Okay, this is awesome. We've got our clean, organized table, but this creates a brand new problem. If I have a table with thousands of students, how can I find one specific person, say Bob, with absolute 100% certainty? What happens if there are two students named Bob in the mechanical department? How do I know which is which? And, oh, it gets worse. What's to stop somebody from accidentally entering Bob's information into the system twice? This kind of duplicate data is pure poison for a database. It completely corrupts our beautiful, clean relation and makes all of our data untrustworthy. We need a rule. We need a guardian. And that brings us to the hero of our story, the key. This one simple concept is the solution to both of our big problems, finding the exact data we want and stopping those duplicates from ever happening. So what is a key? It's basically a special rule we apply to our table. We pick a column, or sometimes a few columns together, and we declare that the value in that column must be unique for every single row. Its first job is to give each record a unique address, which solves our Finding Bob problem. And its second job, because it forces uniqueness, is that it automatically prevents those dangerous duplicates. It's brilliant. Now, keys come in a few different flavors. For what we're talking about today, the two you really need to know are the primary key, that's the main one, the official unique ID for each row, and the foreign key, which is a special key we use to link different tables together. The others, like super key and candidate key, are really just steps on the way to choosing that one perfect primary key. Let's make this super real. In this table, the student ID is a perfect choice for a primary key. But look closely. The email and phone number could also work, right? As long as we have a rule that every student has a unique email, that makes email what we call a candidate key. It's another candidate that we could have chosen to be the official identifier. And this brings us to our last big topic. And it's a very practical one. When you go to pick that primary key, you have a fundamental choice to make, and it's a choice with some pretty serious real-world consequences. You can use a natural key, which is something that already exists out in the real world, like a social security number or an email address. The upside, it has business meaning. The downside, people can change their email address. Or you can create what's called a surrogate key, like a student ID that just counts up 1, 2, 3, 4. It means nothing in the real world, but its huge advantage is that it is guaranteed to be stable. It will never, ever change. And this quote right here just nails the heart of good database design. Stability is everything. A primary key is the permanent anchor for that row of data. You never, ever want your anchor to change. A phone number is a terrible primary key because people change them all the time. A government ID, much better because it's meant to be stable for life. So there you have it. From a simple, unordered set, we built a whole universe of possibilities. We carved out a meaningful table, and we secured it all with a key. Every single time you log into a website or buy something online or post a photo, you are relying on this exact logic. Your entire digital life is identified, located, and protected by these keys, which leads to one final thought. Are the keys that define you built on a rock, or are they built on sand?